Good day, viewers. You are welcome today on the online tutorial class. My name is Mr. Uche Ima, and today I'll be taking you on the topic waves, introduction of waves. Okay, before we proceed, let us quickly look at our objectives for today's topic. The learning objectives for today's topics. By the end of the lesson, the students should be able to 1. Explain the concept of wave and wave motion. 2. Explain the terms associated with wave motion. 3. Explain the types of wave in terms of direction of travel and medium of propagation. 4. Describe the features of wavefront, wavelength, frequency, crest, which is as well known as the peak, trough, amplitude, and wave speed. Then we shall move into progressive wave and stationary wave. Then number 6, we talk about the progressive wave equation. To solve simple problems on the progressive wave equation. Okay, so let's look at the previous knowledge before we go into the topic proper. There are some previous knowledge, some things which you might be familiar with. You should be familiar with the circular motion and simple harmonic motion. Once you are familiar with these, you should be able to give you a better understanding of how to apply some certain equations under the study of wave. So what are these things you need to understand, you need to have knowledge about? You need to have knowledge of circular motion, you need to have the knowledge of simple harmonic motion, some of the equations that are being used there. The first one we have here, we have the formula for angular velocity, which is the angular displacement with time. So with this, we also have this other formula, the angular velocity, which is equal to 2 pi f. We also have angular velocity for 2 pi over t, which is the period. Then over here we have the linear velocity as well, which is the linear displacement with time. Here we have the period 1 over frequency. We also have the period t over n. We have the frequency 1 over the period, which is the inverse of the period, yes. And also, so we have this formula as well, which is a formula for the horizontal displacement of a body performing simple harmonic motion. So all these are formulas applied for the simple harmonic motion, which we also saw a sinusoidal graph or a sine curve. So in this study, we are also going to encounter a sine curve as well. So having gone through our previous knowledge, let us quickly dive into what we have today. Okay, before we go into this, I want us to quickly go through this. Okay, let us quickly go through this particular video. Let's go through this particular video. What we have here is this is the Mexican wave. I think the Mexican wave was first displayed in one of the FIFA World Cup. And what does this actually mean? Let us take the stadium itself as the stadium. Let's take the stadium itself as what? As a medium. And the spectators we have there are molecules. So you can see that as they stand up, they scream, they stand up. As they're standing up, they scream. As they're screaming, those they sit down, the other people sitting adjacent stand up as well, lift their hand, and as it goes, the sound, of course, is moving, but then the spectators themselves are not moving, but the sound is being transmitted as it's moving from one point to another. But there's something I want you to understand, that the spectators are not moving. The spectators are seen to be the molecules or the particles of the medium. They are not moving. Okay, they remain there, in the sense that the the medium is not permanently what stopped, it's not permanently what displaced. It is only the particle that moves like that to and fro and so on. So let us move now into the what definition with what we've just described. Let's move to the definition of what wave, and let us see if it actually relates to what we just the video we have just seen. Okay, wave. The wave says the wave is a disturbance that travels through a medium and transfers energy from one point to another without any permanent displacement of the particles of the medium. So if you actually watch that the video I just showed, the field, the stadium itself is the medium, and the spectators there are seen to be the particles of the medium. So they only move, lift their hands, shout as they sit down. The next, those adjacent to them does the same thing, sit down, and thereby creating a wave. And as they are doing that, the sound is being moved, transmitted like that. Okay, but then the spectator still remains where they are. So that means for every wave motion, for every wave, actually is a disturbance, but the particles, there is no bulk movement of the particle. They remain where they are. Okay, they only go up, down, about that, within that same position. They are not permanently displaced. There is no bulk movement. It's just only a disturbance, and as this disturbance continues and travels along the medium, it is transferring energy. But at the long run, there is no displacement of these particles. The particles remains where they are. There is no bulk movement of the particles. So that is wave. Wave is a disturbance, but the process by which this disturbance transfers energy from one point to another point is what we refer to as wave motion. Why wave is a disturbance? Wave motion is the process, okay, is the process by which the disturbance transfers energy from one point to another in the medium without any permanent displacement of the particles of the medium. Okay, now let's quickly look at the terms associated with wave motion. The terms associated with wave motion. Number one we are going to talk about here is the amplitude. Okay, the amplitude. Okay, now when something is vibrating, I'm always going to use the video I just showed you as a case study. So they move up, they come down. As they are moving up and coming down, they are moving up. That is a center point to which they move up and come down, going across it, up, down, up, down. So they get to a particular height which they cannot go beyond, come down, passes through a midpoint, come down again, like that. So that is how wave moves. Okay, so why this is your center point. So as it's moving, there is a displacement already. It gets to a higher displacement, comes down, gets to another minimum displacement, like that. So at this point, it cannot go beyond this. So that maximum displacement from the equilibrium position, this is referred to the equilibrium position or the fixed position or fixed point. So it goes up, comes down, it doesn't go beyond this, it goes up, comes down. So the distance from the equilibrium position to the maximum displacement, that point which cannot go beyond. So the distance between them from the equilibrium position to the maximum displacement is what we refer as amplitude. Don't forget that your amplitude, which is maximum displacement, it can be again the minimum displacement you have here, which is negative, from the equilibrium position. So minimum displacement from the equilibrium position is also equal to the maximum displacement from the equilibrium position. So from the equilibrium position to the maximum, equilibrium position to the minimum are equal. That can be both referred as as the amplitude. Just as you have here, this is the equilibrium position, this is the highest maximum displacement. Equilibrium position, the highest maximum displacement. So the distance from O to this point is also equal from here to here. So my amplitude is from this 0 point, from this point to this point. It's also equal, the same as from this end to this end. So if I'm giving that the distance from this particular point here to this particular point here is 10 centimeter, what then do you think my amplitude will be? Of course, the amplitude should be 5 centimeter, because when I divide this by 2, from this point to this point will be 5 centimeter. From 0 to this point will also be 5 centimeter. So this is the wavelength. What then is wavelength? What then is the wavelength? Okay, coming to the wavelength now. Wavelength, the distance. Okay, now by the time we move up and down like that, you can see that There is a point here and there is a point here. There is a point here and there is a point here. This point is referred as what? As the crest. Here it's also referred as the crest. And as you move from this end to down to this place, okay, and down back to this place, a cycle has been what? Completed. A cycle has been completed. One cycle is equal to 360 degree, or which is equal to 2 pi what? Radii. Okay, so a distance from a complete cycle is equivalent to what? One wavelength. You can take that as one of the definition. A complete cycle is equivalent to what? One wavelength. But then we have the distance between this crest, from this point here, which is the crest, to this point here, which is also the crest, is also referred as a wavelength because it's also a complete what? Cycle. If you look at this from this end to this end, this is 90 and that 90 and that 90, which is 270, then up here giving you what? And that 90 to make 360, which is a cycle, 2 pi radii. So it's a complete cycle, which is also equal to what? To a wavelength. Coming down here, we have the trough. This point here is the trough, this point here is the trough, this point here is the trough. So this line between two successive troughs is also referred as a wavelength as well. Because from this point to this point is a complete cycle, which is 360 degree, also equivalent to 2 pi what? Radii. Alright? So the distance between two successive crests or two successive troughs is referred as a what? Wavelength. But then it is not always in all cases. But then you should understand that it is not the basic reason why we say distance between two successive crests is because that these 2 points are points that are relatively in the same word phase. They are relatively in the same word phase in the wavefront. So in another way around, if you have 2 positions or 2 points which are relatively in the same word phase, those 2 points are referred as what? As a wavelength, because they make up a cycle. For instance, I have this point here down to this what point. They are relatively in the same word phase. Okay, I have this particular point here, and at this particular point is a wavelength because they are relatively in the same word phase. We are going to see more example on this in the subsequent slides. Now, the next is number 3, frequency. What then is frequency? Frequency is the number of cycles. That cycles is also referred as what? Oscillation. It is also referred as what? Revolution. It can also be referred as what? Vibration. So when I say the number of cycles, I also mean the number of oscillations. I also mean the number of revolution. I also mean the number of what? Vibration that a particle of the medium makes in 1 second. So the symbol is F, and the SI unit is what? Is hertz. But we still have the derived unit. Okay, the derived unit, when they come to this particular point, F is equal 1 over period. So the derived unit for this is what? Is per second. So that per second is what is determined as what? Is what gives us hertz, or what is described as what? As hertz. Alright, there is another formula again which we have at the back of our mind in frequency. So apart from F equal to 1 over period, frequency, please take down this note, put it down as I'm saying it down, because we are going to see some questions that will lead to that. Frequency is equal to the number of oscillation over time taken to complete that number of oscillation. Have you written that down? Put it down. It might not be on the slide, but you have to write it down. Frequency is equal to the number of oscillations over the number of time taken for the oscillation. Okay, so how can we get an oscillation? In your question, they can give you an oscillation directly, okay, or they can give you a graph, just as we have in our previous graph here. Okay, the previous one we have here. Okay, this graph we have here, look at it. Yeah, how can I count my oscillation? 1 cycle is equal to 1 oscillation, or 1 vibration, or 1 revolution. So what is that 1 cycle, which is 1 wavelength? I go from up here, this is half, then down here, this is 1 oscillation, again 1, then down here, this is 2 what? 2 oscillations, down here and down here. So the number of oscillation we have here is 3. So if I have my time here at this point to be what? T equal to 4 seconds, it means that I have 3 oscillations in 4 what? Seconds. Okay, let's continue with our what? Let's continue with the period. Yes, okay. The period is the time taken by the particle of the medium to make 1 complete oscillation. Time taken to make 1 complete what? Oscillation. Okay, just 1 complete oscillation. We have a cycle. time to complete one oscillation. And of course, it is the reciprocal of what? Of the period. The reciprocal of the period. So your period is equal 1 over f. But then I want you to take this other word formula as well. Period is equal the time taken to complete one oscillation. Time taken to complete one oscillation over the number of oscillation. So let's take note of that. Then you can see this equation we have here from our previous knowledge, that the angular velocity is equal to 2 pi over t. So you can calculate your period in this way as well. And your angular velocity is equal to 2 pi f. This is your frequency. If frequency is 1 over t, substitute your frequency here, you will get what? 2 pi over what? T. Okay. Now let's move down to wave speed. Wave speed, or it can be referred as what? Wave velocity. The wave velocity is the distance traveled, the distance the wave has traveled, or the distance, the linear distance that's traveled with time. The linear distance that's traveled with time. V, of course, is the low key V, and we have S over T. And the unit, of course, like every other velocity, meter per second. Okay. Now let us look at how we can derive the very important formula V equal to F lambda. Okay, that is your velocity is equal to frequency times your wavelength. We'll be using much of this equation in these studies. So how do we come about this? We said that your velocity is equal to what? Distance traveled per unit time. But in one complete cycle, my S will now become my wavelength. Okay, because the wavelength is one complete cycle. And the time taken for one complete cycle is by what? Is my period. So if I come over here, I substitute for S, I substitute what? 1 lambda, because it's also a distance. Then for one cycle, then the time for one cycle is a period, which is substituted here. But then I know that my F is equal to 1 over T. So when I substitute 1 over T, F is equal to what? 1 over what? 1 over T. So if I now make T set to the formula, T will now become 1 over F. So when you now multiply F, the lambda is equal to what? 1 over F. So your lambda is equal to what? 1 over T in this case. So F is now equal to what? 1 over T. So lambda times 1 over T. So instead of writing 1 over T, I have F. So F times what? My frequency is equal to what? F lambda. Let me recap that again. V is equal to what? Lambda over T. And we know that frequency is equal to 1 over what? T. Okay? This T is your period. So if I now break this to become lambda times 1 over T, I know that 1 over T is equal to F. So it means that what? F lambda times F is equal to what? Lambda F, or F lambda. So that is how we got this this equation for what? Wave speed. As I said earlier, we'll be using this formula, much of this formula in these studies. So let's quickly talk about ripples. So you can see some ripples here. Okay, when you drop a stone in water, you see the ripples coming up. Okay, a kind of, first you see an impulse, a pulse. The pulse of the particles goes up and then down. Before you know it, it begins to spread. So the small elongated ridges that is being spread out. Okay, whenever there is a disturbance, it spreads out. So that is what is referred as ripples. And pulse is that solid increase. Okay, but it goes up, comes down. It goes up, comes down. Okay, that is what the pulse means. All right. Then, mind you, when you want to understand ripples, pulse, and some properties of waves, which we might not discuss here, if you want to study them better, you can study them using a setup which is called a ripple tank. That we shall discuss later. Now, very importantly, we talk about what? The face. Face. Your face. What then do you mean by face? Let me quickly explain the face here. Okay, we have all these are waves coming like that, coming like that. Now, as we now have another wave coming this way again, like that, and I have the third one coming the same way, like that, and that one again the same way, like that. I find that all these points across all these waves, they are vibrating at the same time. All these points here across in all these waves, they are vibrating at the same time. All these points like that, all these points, the line like this, the lines drawn like this straight, they are referred as what? The wave fronts. They are referred as the wave front. Then all the particles on these wave fronts are said to be in phase. Let me take that again. It can be somehow tricky, difficult to understand. This is a wave, a kind of cross-sectional view of the wave. If I have another one this way, and that one again this way, and that one again this way. Then I now draw this point across. I'm making a line. So all the particles along that line are moving in phase. So the same way here, all the particles along this line are moving in phase. All the particles along this line are moving in phase. That line is referred as what? As the wavefront. The lines are referred as the what? As the wavefront. Then all the particles are in phase. So what then is phase? So particles can vibrate in phase and particles can vibrate out of what? Phase. If I have all the particles here and all the particles here, those ones here and those ones here, they are out of phase, because from this point to this point is what? 90-degree difference. But from this end to this end to this end is what? Is a complete cycle. So they are relatively in what? In the same what? Position along the wave what? Along the wave. So they are vibrating in phase. But B and C are said to be vibrating out of phase. So when you say phase, particles of the medium that are at the same distance from their equilibrium position, that are the same distance from their equilibrium position, that is from here to here, they are said to be what? In phase. Remember, all particles here are vibrating at the same time. So the particles here and the particles here, that are said to be in phase. This and this are said to be what? In phase. Okay? Particles of the medium that are the same distance from the equilibrium position and are moving in the same direction are said to be what? In phase. One, they are at the same distance from that equilibrium position and they are said to travel in the same what? Direction. So all particles along here that are the same distance and are moving in the same direction, they are said to be in phase. But otherwise, apart from this condition, they are moving out of phase. So most likely particles that are moving in phase are basically a wavelength ahead. So let's look at this. We have AE is a wavelength ahead, so they're in phase. What about I? Of course they're in phase. Look at B, look at F. Are they in phase? Of course, because they are one wavelength ahead, 360-degree, 2 pi radii. Then FG, of course, they're in phase. So what about C, G, and K? You find that out yourself. Then come down to that of those out of phase. A and C, are they out of phase? Of course they are, because they are not at the same what? Distances, and they are 90-degree out of phase. Same does B, D, C, and what? E. So I've explained the wavefronts already. Okay, let's take this line. This line is the crest of a certain wave moving down. It is a wave in this direction, waves in this direction, waves in this direction. So, and all these points, these are the point of the crest, the point of crest, point of crest, point of crest, point crest, 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 crest. And if you measure all the crests, they are all on the same what line. Crest, they are all on the same line. Crest, they are all on the same line. So that particular line where all the whole particles are in phase are referred as what? Wavefronts. They are referred as what? Wavefronts. So if this is your crest, then where then now become your what? Your trough. Your trough should be at the middle, in between. Trough is in between. So we have two types of what? Wavefronts. And what are these two types of wavefronts? We have the what? We have the plane wavefronts, and we have the what? We have the spherical what? Wavefronts. So the plane wavefronts usually gives us what? Straight line, while the spherical wavefront gives us what? A curve. Okay, now let's move down straight to what? The types of waves. First, we look at the types of waves in two what terms. Classify it in two ways. The first way, we are going to classify it in terms of what? In terms of the we are going to classify it in terms of the travel, the direction of travel of waves. Okay. Then the next one, we are going to classify that one in terms of the medium of propagation. So let us look at this other one in terms of the direction of travel of wave. In terms of the direction of the travel of what? Waves. Now, in terms of the direction of travel of waves, there are two types, which are transverse waves and we have the longitudinal what? Waves. So how can we distinguish transverse wave from longitudinal waves? Now, the first two concepts that will enable you to understand these two very well is one, the direction of vibration, two, the direction of propagation. So this point here, this is the vertical direction, is the direction of what? Vibration. Then the horizontal is the direction of what? Wave. So direction of what? Vibration, direction of what? Wave. Now I can see here from here that direction of vibration, direction of wave are perpendicular at right angle to each other. So when you have, or when you illustrate or describe such a wave in which the direction of vibration is perpendicular to the direction of wave or to the direction of travel, such wave is said to be a transverse wave. Let's take some example. Water wave, of course, it goes up, down, up, down. The up and down is the direction of vibration, and as it's going up and down, it is spreading, which is the direction of what? Wave. We have the light waves, radio waves, which are referred as what? As electromagnetic waves. So this is also example. Now there are two important positions that have been created in the transverse wave, two important points. And what are these important points? We have the crest and we have the trough. I've explained the crest earlier to you. The crest is the point on the transverse wave where the particles of the medium have maximum displacement. At this point is the maximum displacement from the equilibrium position. But the trough is the position where the position of the transverse wave where the particles of the medium have minimum displacement from the equilibrium position. So it goes like that. So we have taken examples on them. So now let's look at longitudinal waves. Now if you tend to pull a spring, okay, a spiral spring this way like that, okay, you find that the vibration goes pam 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 like that. That's how the vibration goes. Then the vibration goes this way. Then the direction of travel is also the same way as well. Okay, so when the direction of travel of waves is parallel to the direction of vibration of the particle, such wave is referred as longitudinal wave. Example are the sound waves, and stretching was spiral spring. Now there are two positions there, which are the compression region and the rarefaction region. The compression region is a region in which the pressure and the density is above normal. Then the rarefaction region is the region where the density and the pressure is below normal. So what about the normal? When the system is said to be normal, or what happens? All these lines are said to be evenly distributed or evenly spaced. So if they are evenly spaced, at that moment the layers of the molecules or particles of that particular medium is undisturbed. But when it is being disturbed, transmitting wave, it has some compression region and some rarefaction region. So the compression region has a denser and a higher pressure than normal than what it was when it was not disturbed. While the rarefaction have density and pressure less than the normal from when it was being disturbed. So you can still get your wavelength. Just be careful. From this particular point, can you see where it begins? The last end to this last end of the successive compression region is on wavelength. Then look at this point. This is the midpoint here, 1, 2. So if I come to this place, I take 1, 2. So the distance between this end and this end is my wavelength. So the distance must have to be corresponding distance from the compression region and the rarefaction region to give you your wavelength. So this I've explained the compression region and the rarefaction region. Okay, now classification of wave in terms of their material medium, the medium of propagation. Some of these waves require material medium, some do not require material medium. Those that require material medium are referred as mechanical waves, while those that do not require material medium are referred as electromagnetic waves. Example of the mechanical waves include the sound wave. The sound wave, of course, requires material medium, the molecules of the air. Then the waves on ropes, waves in water, water waves, they all require material medium. The air has particles around particles, the water has particles, the rope has particles. It is this particle that transfers this medium. Okay, then so the all mechanical waves, of course, they travel with speed less than that of speed of light. Okay, the other way was the electromagnetic waves travels faster, because all electromagnetic waves travel with the speed of light in vacuum. Okay, so electromagnetic waves do not require material medium, they travel in vacuum. Okay, example, we have our radio waves, microwaves, infrared, and whatever. Okay, the acronym I can give for this electromagnetic spectrum is REGB. Sorry, is RME/G. Okay, RME/G, not REGB. RME/G. RME/G. R for radio, M for microwave, I for infrared visible light, ultraviolet, X-ray, then what, gamma ray. They are all what, examples of electromagnetic what, waves. They do not require material medium, and they are all transverse in nature. Meanwhile, there are some of these waves that are mechanical, require material medium, at the same time they are transverse. They can be mechanical, at the same time they are can be what, longitudinal. So you can start looking at those one before we answer our questions as follows. Okay, progressive wave that moves continuously what, traveling. Okay, they are referred as what, traveling what, waves. Okay, they result from the continuous vibration of particles of the medium. The particles continuously what, vibrating, and they move, spreading out from the source continuously. Then there's another important wave we need to discuss here, and that's the stationary what, wave. So for the stationary wave, it has to do with what, two identical waves. Two waves. When they say identical, that means the waves have the same amplitude, they have the same frequency, they have the same what, time. But in this case, these two waves are moving in opposite direction. As they move in opposite direction, they interfere themselves. There's an interference. Okay, they overlap themselves. They are spy pools. Okay, there is a superposition of these what, two waves as they're moving in opposite what, direction. As they're moving in opposite what, direction. So as they move in opposite direction, they overlap. So when they overlap, what happens? They create some important and interesting what, points. And what are these interesting points? One, they create the node, and they create the what, the antinode. So when they create the node and antinode, the two waves being overlapped remains that way, which is now referred as stationary what, waves. Okay, so such wave we can see from what, the jitter spring. You know, the jitter. By the way, how can we produce this stationary wave? You have a rope fixed at one end, rope fixed at the other end. When you strike, generate a wave from this end, it goes, hits the other one, the other point, and returns back. Hits the other end and returns back. Okay, we can simply say that this is a reflection, rebouncing of wave. So stationary wave occurs as a what, as a reflection of what, of waves. There's a reflection of wave there, but then the two waves must be what, identical. So when this happens, they create a standing wave. That is another name for stationary wave. So the 2 points created in what, in the stationary waves are the node and the what, antinode. So the node is the point where there is what, no displacement of the what, of the vibrating what, particle from the mean position or from the equilibrium position. There is no what, displacement. In other words, there is a zero displacement. So at that point, okay, there is a destructive interference, which we are going to discuss later. But at this particular point here, we have the antinode. This antinode point is where you have what, a maximum displacement of the what, vibrating particle from the equilibrium position. And we also refer this end, the interference created at this particular point is what, the constructive what, interference. So we can mostly get the stationary wave when we strike the string of a jitter. Even in what, in pipes, okay, in musical what, instruments such as what, your saxophone, your trumpet, your flute, okay, the air molecules there can then create a stationary what, wave. So musical notes are actually produced as a result of what, of stationary what, waves. Now, mathematical what, representation of what, wave. For mathematical representation of wave, we have the wave. The wave we have here is a sinusoidal what, wave. Generally, that is a sine wave. It can as well be a cos what, wave, but mostly you'll be coming across what, a sine wave, and height is D represented. So this is the general representation of what, the sine wave. Y is equal a sine theta. Okay, for the sine wave, or y is equal to what, a cos theta. Remember what theta is? From an angle of angular displacement. Okay, angular velocity is equal to angular displacement over time. So if I make theta sort of formula, I would have what, angular velocity times time. So let's look at this. As I said earlier, that the angular speed is angular displacement with time. So from the formula we had that y is equal to what, a sine theta. So looking at this particular formula we have here, angular speed is equal to angular displacement over time. So my angular displacement is now what, when I cross multiply, is what, angular speed times time. So now I take this and I substitute into where we have theta in the previous equation there, and we now have this. Okay, but then there are some particles that will first of all receive the pulse, that will first of all receive the agitation in the medium before the other. Okay, so some wave can be moving particles can be moving before the other receives the sensation and start moving in the same medium. In the same medium. So when that occurs, we have what we call the phase angle difference. And that phase angle difference is either you subtract or you add it up. So this sign here could either be plus or it could be minus. So I want to discuss later, let you know when it has to be plus or when it has to be minus. Alright? But I'm interested in this particular sign phi, which is also referred as phase angle or phase constant or phase angle difference. This phi is directly proportional to the linear displacement. But when I equate it, I introduce my constant k. And this k constant is referred as the angular wave number. The unit for the angular wave number is radii per minute. Don't forget that your angular velocity, the unit is radii. This is the radii, and this is is seconds, radii per second. Why this, which is your wave your angular wave number, is equal to k equal to 2 pi over lambda. So this is the constant. Then this is so 2 pi, the unit is in radii, and your lambda here, unit is meter, so it is radii per meter. Take note of this, you come across it. The unit for angular speed and the unit for for angular wave number. So moving ahead now. So as I said earlier, some particles can move ahead, can quickly get receive the wave, and some can get the wave later. So when it quickly gets particles that quickly get in touch with the agitation of the wave leads, while those that eventually gets the sensation of the wave, receives it later. So when you receive it later, the particles are said to lag. Right, but if you receive it earlier, the particles are said to lead. Then if you are said to lead, as I said earlier, you have either minus or either plus. So if a particle gets it later, then you use negative sign. But if a particle gets it earlier, that means the particle is leading. It leads the particle at the origin. So you use your positive sign here. Okay, so that is what we just said. The particle at A is leading particle at the origin. By what? Distance from here to here is pi. That is half a cycle. Particle at B at this point is lagging because it received the wave agitation later from that at the origin. So it is lagging behind at an angle of 90 degrees. That is quarter of a circle, pi over 2. Okay, so let us quickly take some examples. Number 1, a radio station broadcasts at a frequency of 99.5 megahertz. Please take note of this megahertz. You should be able to know how to convert some unit: mega, kilo, micro, pico, nano, and the rest of them. Now, if this speed of wave is 3 times 10 raised to power 8 meters per second, calculate the period and the wavelength of the wave. Okay, first thing you need to do, take your parameters quickly. All right, have you done that? So let us see. Okay, so these are parameters. F is this, so I need to convert this to the SI unit. Okay, which is I need to multiply this mega to convert to hertz, or to the basic unit. You need to multiply it by 10 raised to power 6. Okay, if it is milli, 10 raised to power minus 3. If it is nano, 10 raised to power minus 9, and so on. So, and what then is the period? If F is given, my period is T equal 1 over F. So when I key in the values, I will eventually have my answer as 1 times 10 raised to power minus 8 seconds. Then the next is to determine the wavelength. Wavelength is lambda. So from the parameters given, I have my F, of course. Is the velocity given? Yes, the speed is given as well. That is this, 3 times 10 raised to power 8. So I now have to use V equal F lambda. So my V, I key in the figure F, which is 99.5 times 10 raised to power 6. I key in the figure times 10 raised to power 6. Then lambda, make lambda the square to the formula here by dividing both sides by 99.5 times 10 raised to power 6, and now get my result as this. Okay. Example 2. A traveling wave in strength is given by y equal 0.03 sine into 2.2 x minus 3.5 t, where y and x are in meters and t is in seconds. Find the amplitude, wavelength, frequency, period, and speed of the wavelength. Okay, the first thing you need to do is to write out the formulas, which the equation, that tallies with this. with the given one. And the equation is what? Y equal to A sine angular velocity times time minus kx. So what I simply need to do is just to compare, to match. So if I'm asked the amplitude, this is the amplitude here. I just match with this. But you should take note, if you are told that y is in centimeter, that means your amplitude is also in centimeter. So you need to convert that from centimeter to meter. If you are told that y is in millimeter, it means that A is also in millimeter. So you convert the millimeter to what? Meters. And what is K? So where can I find that K here? This is where I can find it. So what variable or term is related to this or looks like this, or what can I compare it with here? It is this. So I have it. When I compare this and this, eventually x will cancel x. Then my K will now be 2.2. The unit, of course, is what? Radar per minute. Okay. Then the next question is to determine the wavelength. Don't forget that your K is equal to 2 pi over lambda. So when you substitute the values, 22 equal 2 times 22 over 7, then you solve for what? Lambda, making lambda the solution of the formula by cross multiplying here. Then at the end, I have my answer given here. So how then can we determine? Okay, we have another question. Okay, let's move to example 2. A traveling wave in string is given by y equals 0.03 sine 2.2 x. I hope I've not done this question. Okay, I've treated this question. We've treated that question. Okay, we've treated the question. Okay, this is the continuation of this. Okay, all right. So this is the next one. Example 3. A plane progressive wave is represented by the equation y equal 2 sine into 2000 pi t minus 0.5x. When the symbols have their usual meanings, what is the frequency of the wave? The frequency. So do you have an idea how to go about this? Of course, just the way we discussed earlier, write an equation that suits this. We have several of them. Okay, we have this. A equal, first this is the given equation, then this is the equation that is suitable in solving this. So if you look at this, here that I have x is what can be matched with this, but here that I have t, we can match it up with this. So when I match the entire term here, this omega t, then equal to what? 2000 pi t. If I equate this and this, that means I need to cancel t, needs to cancel what? T. Then my omega, which is my angular velocity, will now be equal 2000 pi radar per second. So it means that my angular velocity is equal to 2000 pi. But then we are asked to look for the frequency. Remember that your angular velocity is equal to 2 pi f. So what then do you do? This is the value for angular velocity. You substitute into this formula we have here. Then what happens? Divide both sides by 2 pi, which is what we did here. When you divide both sides by 2 pi, answer is what? 1000 hertz. Example 4. Quickly try this on your own, then I'll open the next slide for you to check if your answer is correct. Okay, number 4, we've done that. The same situation we have here. We write the same formula as we have here. I'm looking for what? Angular velocity. So as equate what I have here to what I have here, t cancel t, and this is what I have. Then to get my frequency, the angular velocity is equal to 2 pi f. Substitute your values, your key in your values. This is 4, then divide both sides by 2 pi. Then this is what I have as my angular velocity. Then to get my period, I use the formula 1 over what? T. 1 over the period. So make period solve on the formula. I have what? 1 over f. So when you now solve for this, in the long run, finally you have 0.5 pi seconds. So the velocity of the wave is calculated in this form as well. Okay, making v solve on the formula. I have v equal to f lambda. I know what f is. F is what? 2 pi. But then do I know what this my lambda is? No, I don't. So I now go further. For me to get this my lambda, okay, I know that in that particular formula, k is equal to 2 pi x over lambda. I can obtain my lambda from there. So the particular value or variable that is correspond to kx is what 3x in the formula there. So I divide both sides by what? X. So my k is 3. So I come here and substitute what? For 3. So this is 3, or I can use general everything. This is kx, then this is 3x. So my kx is equal to what? 2 pi over lambda, that is k. Then I have the x there already, equal to what? 3x. So making lambda subject to the formula, I cross multiply 3x lambda equal to what? 2 pi x. Dividing both sides by what? 3x. I eventually have my lambda equal to what? 2 pi over 3 meters. Okay. Next, that is solution to number 5. Let's go to number 5 and read the question. A wave travels at a distance of 20 centimeters in 3 seconds. The distance between successive crests of the wavelength is what? 4 centimeters. What is the frequency of the wavelength? Here we are looking for the frequency. The frequency of the wavelength. Okay. The given parameters, we have the distance traveled, 20 centimeters, which you need to convert towards meters. The time in 3 seconds. We have the wavelength, 4 centimeters, which is in what? 0.04 meters. So I'm using V equal to F lambda because that is what it seems to be here. V, how do I get my V? I remember that this is my linear velocity. So V is equal to what? Distance over time. So this is my distance, 0.2. My time is 3. So when I divide, I have my velocity. So that has been taken care of, velocity. Okay. So meanwhile, have it in mind I was looking for what? Frequency. So if this is my velocity, my lambda, my wavelength is 0.04. When I substitute, I get the what? The answer F equal 1.68 hertz. All right, guys, let us see how we can evaluate our understanding. Okay, with these questions. Okay, with these questions, let's take question. The first one, question 1, 2, 3. We are going to use this to answer the question. A wave is represented by the equation y equal to sine pi into 0.5x minus 200t, where all distances are measured in centimeter and time, okay, in seconds. For this wave, calculate. So let us quickly calculate. All right. So what then is a frequency? How would you obtain your frequency? Quickly, let's have you do that. Okay. Your frequency, the answer, of course, should be B. But how can you obtain your frequency? So if you should have this, my take is that 200t. Here I can have what? 2 pi ft. So take everything here, equate it to what? To 2 pi ft is equal to what? 200 what? T. Then make F separate on what formula. I can say omega t is equal to 200t. T cancel t. Omega is equal to 200. Then your omega is equal to 2 pi what? F. Make F separate on the formula. Then you can. Number 2, your wavelength. Answer, of course, should be D. Yeah, D. So how do we go about this? Okay, 0.5x. Around here I have my what? Wavelength. Okay, because kx, I will now have what? 2 pi what? X over lambda. So I'm looking for that lambda. So equate everything you have here to kx or to 2 pi x over lambda. Make lambda the square of the formula. Then number 3, they are looking for the what? For the wave speed. This is very simple. Okay, are you done? All right, V is equal to what? F lambda. So I have my frequency and I have my what? Lambda. So when I put together, plug in the value, I'll solve and have my answer. Okay, as 400 what? Meter per second. Okay, the next question, number 4. Let's quickly take that. Let's go. Number 4. So this is the diagram we have here. Illustrate variation of displacement of y of a wave particle with t. If the velocity of the wave is 250 meters per second, calculate the distance between two successive particles which are in phase. Okay, and how is it going? All right, that is good. Okay, so how do we go about this? When you say what? two successive waves, particles, that means you're talking about the wavelength, two wavelengths. It goes this way to this point. Now I have it. There's one particular way you can simply use. You don't need to. If you want to calculate the distance between two successive waves. So how do you go about this? Okay, let's leave this question. Okay, because the options are not actually right. The options are not truly correct. But fine. Okay, let me just create a question here. How can we determine the frequency? Okay, how do we determine the frequency? Let's forget about the question to the distance between two successive particles which are in phase. So how would you determine the frequency? How can you determine the frequency from what we have discussed? The frequency of this wave. Okay, from there I can use what f equal to the number of what oscillation divided by the time taken for the number of oscillation. So how can I obtain the number of oscillation here? I can count from here to here. This is 1. Here to here, this is what 2. And what is the time for this number of oscillation? The time here should be what? If here is 0.03, this should be 0.04. So the number of oscillation, which is 2, divided by 0.04. Or I can take here, this is 1, and here this is what? Half, 1.2, okay? Sorry, 1.5. Now divided by what? The time taken for the number of oscillation, 0.03. And when you do that, you get 50 hertz. Okay, that is the question. So the question of this number 4 should be: the diagram illustrates variation of the displacement of y of a vertical particle with time. Calculate the frequency of the oscillation. So it is not to calculate the distance between two successive particles. Calculate the number. So calculate the frequency of the oscillation. And the frequency of the oscillation is 50 hertz. Sorry for that. Okay, the next, number 5, the equation y equal a sine into angular velocity times time omega t minus kx represents a plane wave traveling in a medium along the x direction. Given that x is in meters and t in seconds, what physical quantities does the angular velocity over k, omega over k, represent? Okay, quickly do that fast. And what did you get? So let's see what it should be. The angular velocity here, the unit is what? Radar per second. While the wave number, the unit is what? Radar per meter. So when you resolve this, I think what you finally get is meter per second. So from the unit, meter per second, which of them has the same unit here? This is Newton seconds, this is what? Meter per second square, this is meter, and this is meter per second. Of course, the answer is velocity, or it could be speed if you have speed there. Okay, number 6, the distance between what? Between 2 points in phase on progressive wave is 5 centimeters. If the speed of the wave is 0.20 meter per second, calculate its what? Period. So how will you obtain the period? How will you get the period? Quickly, the period, okay, I'm sure most of you got 0.25. So how do you go about the 0.25? So the 0.25, all right, we have your given parameters there. You have your wave speed, okay, you have your wave speed. Then they say that distance between 2 points in phase. The distance between 2 points in phase is your wavelength. So wavelength is given, and you have your what? You have your wave speed. So how would you go about it? So you can use your what? V equal to what? F lambda. Okay. So what then is your frequency? Okay, your period of course should be what? 1 over f. So when you get your frequency, you can be able to get your what? Your period, because period is 1 over f. So you now apply V equal F lambda to get your frequency. Then you substitute into what? T equal 1 over f. Okay, go. Now, which of these waves is both mechanical and longitudinal? Mechanical waves require material medium. Longitudinal waves, direction of wave, vibration are parallel to each other. So which of them have these two properties? Of course, sound. Good. Okay, your radio wave, of course, is mechanical, but it's transverse. Water, mechanical, but it's transverse. Light, out of it, transverse. And also what it is what? Electromagnetic. Okay, number 8. What portion of a longitudinal wave has its pressure above normal pressure? Above normal pressure of a longitudinal wave. Now, if I were told that is a wave above pressure, above normal pressure, okay, which did you pick? Crest, compression, rarefaction, trough. Okay, above normal. So I'll go for compression. Some of you might be tempted to pick this if you're not careful, but then they said what longitudinal wave. If it were to be just wave, I'm looking at this. Transverse wave, I'll go for this. But they said longitudinal wave, so it is the compression region. Number 9, the distance between 2 points P and Q along a wave is 0.05 meter. If the wavelength of the wave is 0.10 meters, determine the phase angle between P and Q in radians. So we are looking for the distance between 2 points P and Q along a wave. So along a wave, that means that is the distance. Okay, distance traveled by what? By the wave. So the distance traveled by the wave is 0.05. That is what we have there. Then the wavelength is what? 0.1. Then we are looking for the distance between them. Of course, the angular distance. As long as we have seen this radian, we are looking for what? The phase angle. So how can we get phase angle? Phase angle. Okay, fine. I give you the formula of phase angle. The symbol is phi. Phi. The phase angle, remember, is proportional to the linear displacement. So when you now equate it, your phase angle phi is equal to what? Ks. K is the constant. And what is that K? That K is fed as what? The wave number. So let's see how you can go about that. I've given you some kind of hints. So take it, your phi is equal to what? Kx. That is your phase angle equal to what? Ks. So what is your K? K is what? 2 pi over lambda times x. 2 pi over lambda times x. So that means you have 2 pi x over lambda. So let us key in the value 2 pi times x. What is the x? The distance moved, okay, from P to Q, which is 0.05, then divided by what? By the wavelength, which is 0. So when you go through this, solve it, your answer then is B, pi. Lastly, the wavelength of a stationary wave is 36 centimeter. What is the distance between a node and the next antinode? Okay, from node to the successive nodes, the distance between them is half a wavelength. Then in between two successive nodes, we have an antinode. So if the distance between the two successive nodes is what? Is half a wavelength. So that means the distance between the node and the antinode should be what? 1/4 of the wavelength. So wavelength is 36, 1/4 of the wavelength is what? That is 36 divided by 4. Answer is what? 9.6 centimeter. Alright guys, I'm so sure that you have acquired much understanding in wavelength. Remember, this is just wavelength part 1. Okay, we have the other series coming up, which has to do with what? The properties of wave and other aspects of it. So if you want to review your answers to see if your answers are actually right, you can just scroll down where you have the solutions to your answers, and then I have to draw the curtain for today's class. Thank you, and God bless you all for listening. Wish you the best of luck. My name is still Mr. Uche.